Good afternoon. Welcome to the final fast pitch session of this summit. My name is Steve Singer, and I'm a program director at ARPA-E. And my colleagues and I will talk today about new ways to harness energy and ways to use that energy more efficiently. So I'm going to pass it off to my colleague, Zach, who's going to talk about a new way to, and an unexpected way, to power a refinery.
Thank you, Steve. So, I think it's pretty evident, especially from the discussions on this main stage the past few days, that there is a heightened optimism for nuclear energy. I don't think it's out of the question that in a few decades, nuclear energy will be as ubiquitous as the fossil fuels that currently power our society. It's time to start finding new applications of nuclear energy. My name is Zachary Berquist. I'm a fellow at ARPA-E, and I think that nuclear energy is more than just an electricity source. It's the best source of industrial heat and has the potential to completely reimagine the way that we do chemistry. I was so inspired by Carlos's analogy yesterday, comparing toasters to data centers, that I decided to make a similar analogy. Refineries are a lot like kitchens. So a kitchen takes a feedstock like a slice of bread and applies heat to it to change its composition to get something that we want, like toast. Think of refineries as industrial kitchens. A refinery takes its feedstock, in this case a barrel of crude oil, and applies heat to it to change its composition to get the fuels and chemicals we use today. The problem is that refineries account for 10% of US emissions and are based off of decades-old process designs. There's a better way. The imminent deployment of advanced nuclear reactors presents an opportunity to not just improve the performance of refineries, but to also nearly eliminate their emissions. This isn't a completely new idea. There are a few projects in development around the world incorporating nuclear into oil and gas infrastructure. But these have only focused on steam and electricity. But the vast majority of the energy demands in a refinery are heat. And that is where we need necessary innovations to enable nuclear to power the entire refinery. So there's two reasons for nuclear. The first is a cost argument. There's this fundamental principle that heat is less valuable than electricity. And this plot on the left shows it. The two cheapest sources of electricity, wind and solar, are still multiple times more expensive as a heat source compared to fossil fuels. Adding on their necessary thermal energy storage, they become cost prohibitive. This is the cost of hydrogen if it meets the DOE Earthshot of $1 per kilogram, and it would still be multiple times more expensive as a heat source than fossil fuels today. I'm not even showing conventional nuclear or next-gen geothermal on this plot because they are not high enough temperature to meet the demands of a refinery. Which leads me to advanced nuclear. It's often seen as a source of electricity, and it can be an expensive one, but nuclear inherently produces heat. And this is the estimated cost of the heat that an advanced nuclear reactor produces. It's by far the cheapest alternative and has by far the lowest emissions. The other reason to use advanced nuclear is in the way that the heat is delivered. Fossil fuels use combustion, whereas advanced nuclear would use heat exchangers, and heat exchangers are a better option. In fact, this is misleading. A heat exchanger can deliver the same power density as a furnace with over 20 times less volume. This is also why alternative fuels like hydrogen and biofuels are less appealing. They use the same delivery method as a furnace. They're just more expensive. The limitations of combustion reveal themselves in the way that a refinery designs its unit operations. So a typical refinery process has three inputs: A feedstock, heat, and a catalyst. These reactions are often endothermic, which means that they cool down as the reaction proceeds. We would ideally like to actively heat them. We want to maintain that high initial temperature, but that's not what happens. Because of the limitations of combustion, a feedstock is preheated, fed through a chemical reactor where it cools down. And then we have to heat it up again, pass it through another reactor where it cools down, and we repeat that process until we finally get our desired product. That's crazy though. That would be like if I wanted to toast my bread. I take Carlos's toaster and I put my bread in it and I turn the toaster on. And then once it gets hot, I turn my toaster oven off and then turn it back on and off. No one toasts bread like that, and no one should do chemistry like that. On the other hand, heat exchangers are much more geometrically flexible. They can deliver heat directly to the catalyst surface, maintaining the temperature in the reactor, greatly simplifying the process, reducing the number of components. It makes this much more capital efficient. Less catalyst is needed because there's higher catalyst utilization, and we can expand the application space to other chemistries that could use this direct active heating. So what I'm proposing is a slight modification to the design of an advanced nuclear reactor system. The heat from the nuclear reactor is removed by the primary loop. This is radioactive. Don't want to touch this. To generate electricity, the heat is transferred to water to generate electricity from a steam turbine. What I'm proposing is that we siphon off this heat to a secondary loop and deliver this heat directly to these novel, integrated heat exchanger chemical reactor systems that do all of the chemistry or cooking that we want in the refinery with all of the benefits that I've already mentioned. I want to drive this point home with this image on the left. This is a furnace at a refinery, and this small orange cube is the equivalently sized heat exchanger that could replace it. This concept has the potential to completely reimagine the way that refineries are designed. But equally important, it should be the way that we power tomorrow's refineries. Nuclear should be the heat source that powers the feedstocks for tomorrow's fuels and chemicals. So if we're going to remodel our kitchen, we're going to need new pots and pans, utensils, and stoves. This could be equivalent to like valves and all the other components, but it's these integrated heat exchanger chemical reactors that are going to be the most important part. There's 4 key considerations that I want to bring up in this potential innovation space. The first is the re-optimization of technical catalysts. This isn't catalyst discovery. This is taking existing catalysts and re-optimizing their incorporation into their support structure to better leverage the improved heat transfer from these nuclear heat transfer fluids. The second is, how do these heat exchangers even look like? What about materials and durability concerns associated with using high temperature heat transfer fluids? And lastly, what about the dynamic response capabilities? We know that existing unit ops can meet the fluctuating demands of a refinery, but can these? The second is, I want to come up with new ways to couple energy to catalysts. If we're going to completely redesign chemical reactors, why would we make them just thermal? There are emerging catalytic augmentation technologies that can greatly accelerate the rate of a reaction beyond that of just thermal alone. So in an existing refinery, heat powers all of the energy, or provides all of the energy necessary to drive these reactions forward. If we can just add on a small amount of energy from catalytic augmentation, we could greatly accelerate the reactions. These can be thermal, photo, or plasma, as Ryan discussed yesterday. Now, it might be unintuitive to use a thermal catalytic augmentation technology in a thermal process, but thermal catalytic augmentation technologies can have secondary effects. So a good example of this was shown by Michael Harold's group at the University of Houston that resistively heated the catalyst in a steam methane reformer and saw a very sharp spike in improvement, likely due to the presence of hot electrons in the reaction. Another group showed that incorporating plasma into a thermal process can greatly improve the performance of a dry methane reformer far beyond that of thermal or plasma alone. So again, the idea here is that nuclear provides most of the energy input, but with just a small amount of energy from a secondary source, it can greatly improve the performance. So there's so many more things that I would like to talk to you about, but I don't have the time. If you work in innovative chemical reactor designs or novel heat transfer technologies or nuclear process integration, then please find me tomorrow at Coffee with ARPA-E. Thank you. Yeah. All right, and with that, I will transfer it to Steve, who's going to talk about endosymbiosis for energy applications.
So I'm going to tell you about the inside story of endosymbiosis, a process from our distant past that will fuel our energy future. So to begin, I'm going to take you back, way back, over 1 billion years ago, when the Earth looked like this. Now, on this Earth, there were just single-cell microorganisms. But these microorganisms are going to be involved in an earth-changing set of events that will lead to the formation of complex life. And I'm going to tell you today about those earth-changing events. But I'm not just here to teach you about ancient biology. I'm going to show you how we're going to harness this ancient biology to reduce our agricultural energy use 30% and increase our ethanol production 33%. So to orient you about endosymbiosis, I'm going to first talk about symbiosis. And symbiosis is the concept of biological cells living together in a mutually beneficial arrangement. And for many of you, the most familiar symbiosis is the one you have with the microbes in your gut, the human microbiome. So symbiosis is just a general term. Endosymbiosis is a special term for a cell entering and living in another cell. So endosymbiosis is the foundation of complex life. About 1.5 billion years ago, 2 microbial cells got together and formed the mitochondrion. Now, the mitochondrion is the energy center of the cell, and almost all life is powered by the mitochondrion. Everything from mushrooms to whales. But nature wasn't done yet. About 1 billion years ago, one of these primitive cells had a cyanobacterium, which is a bacterium that grows on carbon dioxide and light, enter and live in this primitive cell, forming the chloroplast. And now the chloroplast is the center of light harvesting and photosynthesis in almost all organisms. Everything from single-cell algae to redwood trees. But there are more symbiosis and endosymbiosis in nature. Cyanobacteria are really promiscuous. They form these endosymbioses with organisms throughout the kingdom of life. And last year in Science, there was this really beautiful paper that showed an ocean-going algae had, in addition to the mitochondrion and the chloroplast, an additional endosymbiotic association. As you see in the image on the top, the sphere at the top of the cell was actually a nitroplast, derived from a cyanobacterium that fixed nitrogen. And it divided along with the mitochondrion and the chloroplast in the cell. So what you see in the image on the bottom is that the mitochondrion, the chloroplast, and the nitroplast combine to take light, carbon dioxide, and nitrogen and grow the cell. So endosymbiosis is not just really interesting basic biology, but actually we can apply it to make agriculture more efficient and more sustainable. So in Asia, on certain rice fields, you see on the surface of the flooded fields an aquatic plant called izola. Now, if you take the leaves of the izola and look at them at microscopic depth, what you see is a filamentous cyanobacterium. And that filamentous cyanobacterium fixes nitrogen. And so, like the nitroplast in the previous example, this allows the izola to grow in the absence of fixed nitrogen. More importantly, the nitrogen that it fixes can be given to the rice plant so it can grow. So you don't need synthetic fertilizer. So if we look at that relationship, what we realize is, wait a minute, if we took the capability of the izola with the cyanobacteria and got the cyanobacteria to actually form an endosymbiosis with the rice, then we don't need fertilizer and we don't need the izola, and we'd have nitrogen-fixing hybrid plants. Now for us, I think in the United States, the most important crop is corn. So if we could do that for corn, it would be revolutionary. We'd have no nitrogen fertilizer needed. That would allow us to save 0.5 quads of energy and lower US emissions 3 to 5%. And the reduction in agricultural energy uses of 30% comes from saving 0.5 quads of energy. So if we want to take a system where we now apply all this synthetic nitrogen fertilizer and replace it with nitrogen-fixing hybrid plants, we need to do research and development in a number of areas. So it sounds easy, but it's really hard for a bacterial cell and a plant cell to interact and the bacterial cell to enter that plant cell. So we really need to figure that out. After they enter have the cellular interaction, we need to take those single plant cell hybrid interactions and grow the plant cell to a full plant, which sounds easy, but it's also very difficult. Finally, if you think about the azolla plant localizes the filamentous cyanobacteria in its leaves because it can take light and fix nitrogen, and that provides a limitless amount of energy. So if we were going to develop these nitrogen-fixing hybrid plants, we need to figure out how to do that in something like a corn plant. So you may ask, can we do other design symbiosis? And it turns out we can. So I show an example here of a cyanobacterium that was engineered so it could enter and live in a yeast cell. And the importance of that is that yeast cell could now grow with carbon dioxide and light as its source of energy and electrons, because the cyanobacterial endosymbiont made the energy and sugar it needed to grow. So looking at that, we realized, hey, wait a minute. These yeast cyanobacterial hybrids, we could use them for ethanol production. We could perform 100% conversion of sugar to ethanol. And that would improve ethanol production by 5 billion gallons. And if you think about we maintain current ethanol production, that would free 12 million acres of agricultural land for other uses. So the increase of 5 billion gallons is a 33% increase in ethanol production. So I'm going to show you how we're going to get to 100% conversion of sugar to ethanol. So in a conventional yeast fermentation, which is how ethanol is made now in the United States, you take sugar, you add yeast, and you get 2 molecules of ethanol. But you get 2 molecules of CO2, and that's a third of the carbon that's driven off by this process. What happens if we have our yeast cyanobacterial hybrid? Then if we shine light on it, we can actually deliver electrons and energy and fix that third amount of CO2, performing 100% conversion. Again, we need a lot of research and development. We need to figure out how these hybrid cells actually work and do cell biology. We need to be able to actually engineer the metabolism of these hybrid cells to make them work the way we want to. And finally, we need to figure out how to add light to ethanol fermentation in a cost-effective way and perform bioprocess to optimize it. So, this concept may seem a little far-fetched and daunting, but I think we can take inspiration from nature. Nature used endosymbiosis for power and converting light to energy. Those are 2 essential features that we want to do in our energy future. So if you're passionate about applying biology to energy and engineering natural systems, please come talk to me tomorrow, or you can email me and I'll be glad to talk about it. So now I'm going to hand it over to my colleague Charlie, who's going to take a different journey into the past.
All right. Hello, everyone. I'm Charlie Werth, Program Director here at ARPA-E. Today, I'd like to talk about electrification of water treatment. Specifically, I'd like to talk about how we can use electrochemical processes to treat drinking and wastewater. Before we get started about what can be, however, I'd like to go back. Not a billion years like Steve, but let's just go back to around 1850. That's when John Snow, the father of epidemiology, discovered that the Broad Street well was a source of cholera in London, England. He did this by painstakingly mapping out, going house to house, where the cholera cases were, they're shown in red, and finding that they were clustered around the Broad Street well that's circled in blue right there in the center. He also found that that Broad Street well was being impacted by sewage. People were dumping their sewage in the basement, they were putting out in the front yards, and it was leaching into those wells. That pioneering discovery allowing Jyotsna to discount that airborne particles were the source of cholera, and more importantly, led to the use of chlorine at the turn of that century as a powerful disinfectant to remove pathogens from drinking water. That was a huge advancement in public health that's affected every one of us. But now, 125 years later, we're still using chlorine and many of the same chemicals in water and wastewater treatment. Shown here are the top 10 chemicals used in drinking and wastewater treatment. They include coagulants like alum and lime, disinfectants like chlorine and sodium hypochlorite, the base, sodium hydroxide, and then dechlorinators like sodium bisulfite. On the right is a cartoon of a drinking water treatment plant, of course simplified. We use coagulants early in the process. They're used to aggregate out particles and settle them so that they don't shield or protect pathogens and other pollutants from downstream treatment processes. We use disinfectants because they're powerful oxidants, and they can inactivate bacteria or viruses, and they also can destroy micropollutants or other things that can harm us. We use the base, sodium hydroxide, to control pH during water and wastewater treatment, and we use dechlorinators not so much in drinking water treatment, but we use it in wastewater treatment, where we still disinfect the wastewater, but we have to get rid of that residual chlorine, because if we discharge it to surface water, it harms the local ecology. Now, all of these chemicals are produced at centralized locations and then distributed to the almost 20,000 drinking and wastewater treatment plants in the United States. These chemicals come with a large energy and CO2 equivalent emissions impact. And we're going to illustrate this with a plot below for 4 of these chemicals. There's chlorine, sodium hydroxide, hydrogen peroxide, and sodium bisulfite. So the energy impacts are on the left vertical axis, and then the CO2 equivalents on the right. What we see is that the energy equates to about 0.4% of the US energy budget, and that results in about 40 million metric tons of CO2 equivalent emissions per year. We have an opportunity to reduce these impacts by improving these production methods, and also by producing these chemicals on site and on demand at drinking and wastewater treatment facilities. And our goal is to reduce them where these red bars are, more than half. We can also look at the transportation impacts to see how it affects the energy and the CO2 equivalent emissions. So let's look at chlorine as an example at the bottom left. You can see where we synthesize chlorine in the United States, and there's several dozen locations. On the right's just drinking water treatment plants, and there's about 15,000. That means we have to store, transport to all of these locations, and then store again before usage all of this chlorine. If we look just at chlorine, hydrogen peroxide, the sodium hydroxide, and the sodium bisulfite alone, they're responsible for more than 4 billion freight ton miles annually. We can also think about safety impacts. We're all familiar with chlorine gas spills from railroad tank cars. There's been a number of incidents in the news, and here's a photograph of one. We're also familiar with the impacts financially, such as lawsuits and other actions. If we look at the Chemical Incident Tracker database, we find that since 2021, there's been 61 major chlorine releases. 20 of these have caused injuries and death, and 24 of these have caused evacuations. So I propose it's time to replace these energy and emission-intensive chemicals with electrochemical processes. And so let's take hydrogen peroxide as an example. It's produced through the anthraquinone process. We start with natural gas, and through steam methane reforming, we form hydrogen. Then that hydrogen enters to a redox cycle with anthraquinone so that we convert oxygen into hydrogen peroxide. Just the first part of this energy-intensive reaction requires a temperature in excess of 800 degrees. So what if, instead, we can produce that electrochemical? We have readily available electricity, and then in situ, on site, on demand, we produce that electrochemically. We produce hydrogen peroxide, we produce chlorine, we produce whatever chemical we need. Fortunately, there's results in the literature that show this is entirely possible. So on the left is an image from a journal paper showing that we can use boron-doped diamond electrodes with niobium, and we can convert water directly into hydrogen peroxide at a low potential. On the right's another approach, where we have palladium on carbon gas diffusion electrode, where we convert oxygen into hydrogen peroxide, and then over a palladium catalyst, convert that into an even more powerful oxidant, the hydroxyl radical. There's also results in the literature showing that we can have the energy needed for chlor-alkali production, which is already an electrochemical process, by using promising bipolar electrodes. As far as I know, however, there are no drinking water treatment plants using at-scale electrochemical processes. There are some industrial applications of wastewater, but in terms of municipal wastewater, there's almost nothing out there that I'm aware of. The main challenges are reaction selectivity, electrode stability, energy efficiency, and scalable flow-through process or reactor design. And so let's look at selectivity, and that's what I'm trying to illustrate on this plot on the right. So we start with oxygen, and let's say we want hydrogen peroxide. If you look at that free energy diagram, it's an intermediate. So we want to select for that, even though the oxygen radical, the hydroxyl radical, and water are all more thermodynamically favored. Let's think about this electrode stability challenge. And so here I try to illustrate this on the bottom right. Shown there are common electrode materials. Up above that are some of our most problematic or challenging water pollutants. Some of them require very high potentials. For example, look at PFAS or forever chemicals. At those high potentials, we start to corrode almost all of those electrodes. Now, the exception there, or the gold standard, are boron-doped diamond electrodes. But then you think about the amount you pay for drinking water at the tap, and you realize, no way can we use those. It's about a penny a gallon. Electrochemistry also allows us to expand our water treatment options. So think about the standard water treatment chemicals we use. Those are shown in the shaded area at the top. They come at fixed potentials. Now, different pollutants have different potentials needed to destroy them. So imagine if we could tailor our chemical process so that we would choose the potential of the species that we produce to destroy the pollutant of interest. Or better yet, just directly reduce or oxidize it at the electrode, at that required potential. So, the water treatment is very large. It's important to each and every one of you. There are very, very few things we need beside water to live every day, except air, of course. I'm interested in talking with electrochemists, water experts, or anyone who's interested in how to electrify water treatment. So please come talk to me tomorrow at the ARPA-E coffee. Thank you. All right, I'm going to hand it over to my colleague, Dr. Sharma, who's going to have a cool twist on fracturing.
Thank you. Hello, everyone. My name is Jyotsna Sharma, and today we will discuss how innovations in fracking can unlock even greater energy production while also locking away carbon. Welcome to the future of fracking. But before we dive in, let's start with a quick energy trivia. What process is used to store over 100 billion tons of a material, 100 million rather, tons of a material in deep underground formations in the US each year? So how many of you think I'm talking about CO2 sequestration or carbon capture and storage? If I can see a show of hands. Okay. Well, that would be an incorrect answer because currently we only have the operational capacity to store about 22 million tons of CO2 underground in the US annually, which, by the way, is less than 1% of our CO2 emissions, which are about 6.3 billion tons. So there's billion here. The correct answer to this question will be hydraulic fracturing, also known as fracking, a technology that has revolutionized energy production, making US the #1 producer of oil and natural gas globally. And during fracking, along with water, we inject millions of tons of solid proppant material, which is typically sand or ceramic based, to keep the fractures propped open, hence the name proppants. And a majority of this injected proppant stays in the ground forever, so we are effectively sequestering it underground. And currently we use about 135 million tons of proppants every year in US alone during fracking. So given this massive gap between our CO2 emissions and the sequestration capacity, what if we could significantly boost the production from hydraulic fracturing and simultaneously address the carbon storage challenge using proppants? Let me show you how we can achieve both these objectives through innovations to shape the future of fracking. So during the hydraulic fracturing process, we inject large volumes of fluids, which is primarily water mixed with chemicals and proppants, down into a wellbore at high pressures. And this creates fractures in the target rock formations. In fact, currently about 70% of the US oil and gas production is enabled using the hydraulic fracturing technology. However, it's not just used for hydrocarbon production. Even enhanced geothermal operations rely on fracking to extract heat from hot rock formations. And during this process, we inject on average about 20 million pounds of sand or ceramic-based proppants per well. And these proppants play a very important role in the overall production performance because they prevent the fractures from closing due to the reservoir pressures and provide a conductive pathway for fluids to flow from the reservoir into the wellbore. So what if we replaced these traditional sand or ceramic-based proppants with a carbon-rich material? The goal will be to first and foremost significantly improve the production performance from hydraulically fractured reservoirs. Because in spite of the tremendous success with fracking, there are still many challenges. For instance, currently we recover less than 20% of oil and gas from unconventional reservoirs because of their very low permeabilities, leaving behind over 80% of shale resources underground. The production rates decline very fast within the first few years, as you can see from this typical production profile from a shale oil well. And millions of gallons of water is required during the fracking operation. At the same time, by using carbon-rich material as a proppant, we could enable long-term storage of CO2 in a stable solid state as a proppant, which will minimize the risk associated with leaks, which is often a big challenge in traditional CCS operations where CO2 is stored as a supercritical fluid underground, which can easily leak. We will also save on the drilling costs by utilizing the millions of existing wells, which are already producing using fracking. So this can be a more economic as well as more effective way of doing carbon sequestration as compared to traditional CCS. Now, one option for the carbon-rich material that we could consider as a proppant to meet both these objectives could come from this, which might look like a beautiful mountain from a distance, but this is in fact a heap of petroleum coke, also known as pet coke, which is a byproduct of the petroleum refining process. And currently we produce about 50 million tons of pet coke in US each year. And since this is over 90% carbon, when this is burnt as a fuel, it will produce about 185 million tons of carbon dioxide annually. In fact, short coke, which is considered one of the most undesirable forms of pet coke, is far worse in emissions even as compared to coal, when burned as a fuel, producing up to 3 times more sulfur dioxide, more nitrous oxide, as well as more carbon dioxide. So sequestering short coke as a proppant rather than burning it as a fuel will certainly make sense from an emissions reduction standpoint. And it turns out that short coke also has many desirable properties to improve the production performance from hydraulically fractured reservoirs. For instance, their uniform size and roundness improves the fracture conductivity, which enhances production. They have lower density as compared to the traditional sand proppants, which minimizes the risk of settling in the wellbore and also reduces the amount of water required during fracking to transport these proppants. They have high hardness index, which enables them to withstand the reservoir closure pressures. And they can be sourced locally from refineries in Texas, Oklahoma, and Louisiana at a price point quite similar to the traditional proppants at few cents per pound. And while using these as proppants might sound like a long shot, no pun intended, petroleum coke was in fact recently used as a proppant during hydraulic fracturing in a field trial, and it resulted in a 15% improvement in recovery, which shows that there is a precedent for using carbon-rich material as a proppant and getting improved production performance. However, innovation will be needed to significantly improve the recovery efficiencies because we are still leaving behind over 80% of shale resources underground. An additional improvement could come from things such as engineered proppants, where they are infused with chemicals or coatings that can further enhance the flow of hydrocarbons from these very low permeability reservoirs. or even explosive propants that can create secondary and tertiary fracture networks to further improve the overall recoveries. However, engineered propants can be up to 10 times more expensive as compared to the commonly used sand propants. So cost-effective technologies will be a key to improving the recoveries. And there are other options for carbon-rich materials that can be leveraged. For instance, we can use biomass waste in the form of biochar, or even mineralized CO2 using naturally occurring rocks that react with CO2 to form stable carbonates such as basalt or olivine sands, or even carbon black, which is a byproduct of the methane pyrolysis process. However, innovation will be needed to make any of these materials suitable for use as a propant, which would require them to have high crush resistance, thermal and chemical stability, low density, as well as cost effectiveness, among many other criteria. And now I would love to hear your ideas on how we can significantly boost production from hydraulic fracturing and simultaneously lower its carbon intensity. We can chat more tomorrow at Coffee with ARPA-E, and please don't feel intimidated by my name, that is. You can call me Joe, and I look forward to hearing from you. Thank you.
Okay, this is just a reminder to send us questions through the app. We're eager to answer them. So I think I will start off with Zach and have a question. How can we use nuclear waste as the heat source for our refinery reactions?
Yeah, we've actually talked to a few people about this. I want to make sure I understand the question. If we want to use the radiation directly from the decay of nuclear fuel, that's an entirely different concept, which I think could be explored. It's just a little bit outside the scope. Otherwise, it's actually kind of source independent what the nuclear is. So really the point of the program is that you can come with the heat can come from an or a high temperature gas reactor, sodium, molten salt, you name it. As long as that heat is above about 550 C, we don't really care where it comes from. So we're pretty agnostic.
So I have a follow-up.
Yeah.
What do you envision as the size? I mean, I think Bill talked a lot about size of reactors this morning.
Yeah, so a refinery, these large chemical facilities, they're on the order of like 100 to 1,000 megawatt thermal. So an SMR is somewhere on the order of 300 to 1,000 megawatt thermal. So it's really maybe 2 to 3 SMRs can power one of these facilities, and you would want that redundancy. So the size actually also lines up pretty well.
So Charlie, what is the efficiency of PFAS destruction using electrochemistry?
What a good question. A little bit off topic, but I'll attack it here. There are different technologies for destroying PFAS. The electrochemical option, it's a function of time. You can certainly destroy, let's say, 90, 95%. When you get really low concentrations, the thermodynamics get a little less favorable, but you can destroy the majority of it given enough time. So it's the kinetics which really slow you down. There are other issues as well. You have to make sure your water's not acidic and you don't get fluoride buildup or you're going to get HF. That's a bad thing. But yeah, different challenges.
So this might be a good opportunity for you to talk about your interest in PFAS in general.
Certainly, yeah. I think there's a lot of energy challenges with PFAS. I mean, we have extensive PFAS, I think, contamination across the U.S. in terms of energy inputs needed to potentially address all of those sites and to provide clean drinking water and clean wastewater. It's a big challenge. There's been restrictions in terms of applying sludge onto land. And so there's energy challenges associated with how do you treat that sludge? Do you destroy it? Do you oxidize it? Now that you can't land apply it in some states. And so there's a whole suite, I think, of new challenges coming up with that.
So Joe, what would be the balance of CO2 stored versus CO2 released in the fossil fuels being released? Net negative or net positive?
Well, so here, like what I'm focusing on is currently we are doing fracking, a lot, and at least in the near term, we will continue to do, produce from hydraulic fracturing. So can we use this process, like right now we are not using, it to store carbon. Can we at least abate some of that CO2 and reduce the carbon impact? So even if it is not going to completely make it net negative or net zero, it is still going to make a huge impact, especially because we are using millions of tons of propellant. A lot of people don't realize the amount of the solid material that actually stays in the ground, and it's in the order of millions of tons. So I think that gives us that opportunity to potentially store carbon. And even, again, as I mentioned, even if it does not come out to be completely net zero, I think still that will be a step in the positive direction.
Can you talk about, like, where the carbon comes from will change the net positive or negativity? So.
Absolutely, yeah. So the example that I gave with petroleum coke, that will be an example of maybe CO2 abatement, where since short coke is a far worse fuel even as compared to coal. So if we take that off from the burning application and put it in the ground, we are potentially abating not just CO2 but even other gases which are pollutants like sulfur dioxide and nitrous oxide, and it also has many heavy metals. So in the context of environmental pollution, we can reduce that. So that will be an example where we are abating CO2 versus if we talk about biochar, for instance, that will be direct CO2 reduction. So yeah, depending on what material is used, the overall calculation for the carbon allocation will be slightly different.
Thank you. So I have a question for me. So what must be done to the nitrogen-fixing bacterium and the host yeast to prevent them from killing one another? Aha. So one thing I didn't tell you is that I elided this topic, is that the yeast cyanobacterial hybrid didn't survive very long. So it actually may have been killed. So that's really true. We're going to have to figure out ways so they live together without killing each other. Okay, so that's like the odd couple, but maybe that's a really old reference. So I think one interesting way that I've seen is that you can redesign the genome of the cyanobacteria so that the yeast will recognize its DNA and replicate it. So it will think it's actually part of the yeast system. So one of the other issues that might occur is that the cyanobacteria or the yeast makes metabolites that would be toxic internally to the other. And I think this is an example of we can combine engineering with evolution. Now, that has become a powerful tool in metabolic engineering where you use evolution, and you can automate it to just keep growing cells until they adapt to a new situation and they pick up mutations that will allow it to survive. And so, the yeast as long as it can replicate under the conditions and you can figure out how to automate it, you might pick up a population where both the yeast and the cyanobacteria mutate together to form a hybrid system. So let's see. Zach, nuclear or not, have any of the augmentation technologies been commercialized to refinery or near refinery scale anyway? And not just including nuclear, but plasma, microwave?
Yeah, there's a few companies that are working on this around the world. I know probably the most notable example is a company, Topso. They're working on an electrified steam methane reformer. But again, with electricity being the primary energy input, it's difficult to see that being cost competitive with something that is providing, where heat is the primary input. So that's, yeah.
So, Charlie, do you have a vision for how wastewater utilities would adopt these new ECAM approaches? Would they be receptive to on-site production? Would they contract with a company to achieve this?
Yeah, I think the utilities are fairly conservative, right? It takes time to work with them to integrate in new technologies. I think often with utilities, they certainly have expertise in conventional wastewater treatment, but most of the time they contract out for specific technologies or for builds when they integrate new processes into their system. So I think the approach would have to be, one, doing a pilot study for, let's take, for example, chlorination, and you're doing it on-site electrochemically. The chlorination process would happen presumably after, toward the end of the treatment system. The water is relatively clean. You're trying to kill the residual kind of pathogens that are in the water. You add that chlorine electrochemically, you have a side stream which you would treat and show a demonstration. I think that gives them confidence. It also helps with the design that then a specialized firm or companies would have to then modify and improve and then work with the regulators as well to show how that would be implemented. And probably in the early stages, you'd have to have backup chlorine, right? Just, the regular chlorine chemical, so that if the electrochemical system went down, you'd have a backup and a fail-safe, and then eventually you could move over.
Joe, propants are different for oil and gas and enhanced geothermal. Would carbon-rich propants be useful for enhanced geothermal as well as traditional fracking?
Certainly, that's the vision, and hopefully, we are right now envisioning a program that will capture all those different spaces where fracking can be an enabling technology, be it geothermal or even geologic hydrogen. That fracking might play a very important role in all those processes. So if we can have these carbon-rich materials or method of storing carbon dioxide using these propants, it will certainly be very helpful. And that's where we want those innovative ideas to develop a material that can withstand high temperatures, which is a key concern in geothermal reservoirs, like propants that can withstand high temperatures and high pressures as well over a long period of time. So certainly, I think with innovation and right combination of materials and even the operational processes, I'm hoping we will figure out a way to develop those propants that can be utilized.
So for Zach, how close does the SMR need to be to the industrial plant?
Yeah, there was an analysis done by EPRI about basically how far heat could be transferred where it would still make technical and economic sense. It's actually up to like 20 kilometers. So in terms of the distance needed to actually maintain that like low temperature drop, it's pretty far. Now, in terms of regulatory concerns, we always like to refer people to nuclear submarines, where they actually place the missiles closer to the nuclear reactor core than any oil on board. So we should be fully capable of integrating nuclear SMRs very close to chemical and refinery plants because we are clearly capable of doing it in a much denser packed space in a submarine.
So thinking about like a specific refinery, would a single SMR serve multiple furnaces in the refinery?
Yeah, so I think that's somewhat of an open question. So I should also make the shout out. We're in this program development with Corey Phillips, the program director. So one of the theses that Corey's also brought up is just like buying something off the shelf. So if you bought a micro reactor, something that was on the order of 50 megawatt thermal, that could directly supply its corresponding unit operation. Otherwise, if you're using an SMR, yes, it would be supplying the heat and electricity and steam to multiple unit operations.
So this is a question for me. Why not transfer chloroplasts from plants into yeast rather than putting the modern cyanobacteria into the yeast cell? Chloroplasts seem to already exist as an organelle. It seems like it would be better adapted to living inside a cell rather than trying to manipulate cyanobacteria. So that's already been done, and it works kind of as well as the cyanobacterium example that I showed. But what I think I'd be more interested in the cyanobacteria because there's a larger variety of cyanobacteria, and you can imagine having, many different opportunities to find one cyanobacteria that could be adapted to live in a yeast cell. And also, thinking more broadly, it's not just ethanol that we could produce. We could also produce chemicals, and I think there will be some limitations in engineering the chloroplasts. So my thought is that the cyanobacteria might have more variety and also be more easily engineered. So let's see, Charlie, how does the economics of electrochemical production on site compare with the economics of scale production of chemicals traditionally?
Yeah, that's a good question. I think certainly we're looking at literature results to try to gauge this economic viability. I think a lot of it depends on the stability of your electrochemical process, and specifically if you're looking at the catalysts that are part of the anode or the cathode. Oftentimes those replacement costs dominate or the maintenance just required to service that. And so in many, I think, literature papers where you're looking at electrochemical processes, if you assume very optimistic scenarios in terms of today's technology, in terms of the catalyst or the electrode stability going out for years, it's very favorable. But when those things start to fail, and if we don't, I think, troubleshoot those and find ways to make them very durable, then the costs just aren't competitive. And so that's a big challenge, is trying to design these electrochemical processes so that they are favorable. Yeah.
Thank you. Joe, is there any aspect of improved high carbon propants that could reduce the quantity of water in the fracking process? It seems this is nearly as troublesome as a negative consequence of fracking.
Yeah, certainly the amount of water used and produced is a challenge in hydrocarbon, shale production. So I think with the propants, one of the opportunities is that when you have propants that are lower in density, you require less water to transport them. So you can have reduced amount of water required. But in terms of the produced water, that remains a challenge for the industry, because for every barrel of oil that we produce, oil or gas, we are producing up to 5 barrels of water, which is highly, it's very salty, 4 or 5 times saltier than ocean water. So the treatment of that water and maybe some of Charlie's technologies can be utilized there. But yeah, I think the relation between the propant and the water is like, if the propant is lower in density, that reduces some amount of water required, because you don't have to transport that. It's easier to transport lighter propant farther into the fracture with less amount of water.
So Zach, is there a first refinery that this would, or a first industrial plant that the nuclear reactors would be the most appropriate to site, or the lowest hanging fruit?
I'm not sure I have the answer to that necessarily, like a specific site called out. We've identified like certain processes within a refinery that might make the most sense, or other chemical processes. So like again, like Dow and X Energy have already established a relationship. X Energy is building one of their Gen 4 reactors to provide steam and electricity to Dow's Seadrift, Texas plant. So since that infrastructure is already there, maybe they could also start supplying some of the heat. So I guess that could be one option. Otherwise, these refineries are so large, obviously, it'd be a huge capital investment. It's likely going to start on their testing facilities before it ever got to that scale. But I don't have an answer for a specific site for first mover.
So this is a question for me. Do you anticipate an intracellular competition for energy resources between the nitrogen-fixing cyanobacteria in the plant, and thus leading to a reduction in the yield of crops? I could say that eventually we would figure it out, but I think that it would probably initially lead to a reduction in crop yield. But honestly, if we could get cyanobacteria to fix nitrogen and give it to a crop, I think that would be so transformative, it would be worth going through the lower crop yields. If you think about, we need to get these plants to have cyanobacteria in them, we need to get them to grow as plants, and we need to be able to localize them into the leaves. So all these things are significant technical challenges. So I think even before we think about the technical challenge of getting the crop yield to be the same, we have to overcome all these other technical challenges. So let's see, so I think, Charlie, chloralkali is already an EChem process. Is there a reason the process hasn't been modularized and distributed in the past?
I think there are certainly efficiencies of scale. And so, and then there's also I think it's just a historical precedent. And so you have large chloralkali production facilities. As you saw on the figure that I showed, or the image, there's several dozens across the US that produce them. And they do it cheaply. Likely, I think you'd have to change your reactor design at the wastewater or drinking water treatment plant. But using that same process, certainly they're doing it cheaper where they're at. They also consume a lot of electricity, and so perhaps they're located near electricity sources. That said, I think theoretically there's no reason you couldn't do it at least as well or less expensive at a drinking or wastewater treatment plant with design modifications, and maybe even improve on the process. I think one of the promising, emerging approaches is using bipolar electrodes, which show that you can reduce the energy by half for conventional chlor-alkali processes. So there's certainly some advancements can be made, but also modifications would have to be done.
So, Joe, if we use the pet coke for propants, is there a need for additional resource extraction to make up for this as a source diversion?
Well, so yeah, that's a good question, because like right now, one of the major use of pet coke, I mean, it is exported out and generally used for burning as a fuel for different processes. But the idea is like, can we use a cleaner source? And certainly, that wherever it is being burned currently will have to be replaced by some other fuel. But given that it is far worse than even coal in terms of the emissions, even if we replace it by coal, hypothetically, it's still an improvement in the overall emissions. But hopefully it can be replaced by a much more cleaner burning fuel, such as natural gas, which will be the ideal, or renewables one day.
Or nuclear.
Or nuclear, yes. But natural gas will be the low-hanging fruit in terms of the replacement.
So this is a follow-up to Zach. Does the heat source actually have to be nuclear? Could it be geothermal? Are there other heat sources?
Yeah, so the problem with it's really just a match of the temperature and then the temperature demands of the process, right? So it's not that, look, if a geothermal well can supply heat at 600 degrees Celsius, we would welcome it as an option. But I mean, right now, even with ARPA-E's current efforts, we're trying to push geothermal to 375, and that's simply too low to do a lot of the chemistry we need.
That would be super, super hot,
yeah,
right?
Yes. Yeah, exactly. Yeah.
Oh, yes, we're out of time. I have all these questions still to ask, but I think we're out of time. I think we should thank the speakers and thank all the speakers in the Fast Pitch sessions.